record this. Okay, so we are talking about log of n. And that is the big O notation that allows us to, or it's a different way of how we can express the time it takes. Remember, just for big O is just the time it takes for your algorithm to run. And so if you guys remember back in the day, I talked about just a visualization of how these all work, where we've got O of n. So this will be size, which is represented is n. And this is time, right? And this is how long it takes. And so this is O of n, right? So as n increases, it is linear, or the time it takes to run an algorithm is linear to the time it takes, or the size of my array. So as n increases, the time it takes increases. These are your for loops. These are us iterating and having to check every single value to make sure, to see if everything's in there. If we've got an array of 1, 2, 3, 4, and I want to see if the value of 3 is in here. Remember, time complexity is the worst case scenario. These aren't ordered, and the worst case is 1, 2, 4, 3, or something of the nature, some sort of combination where 3 is at the end. And I do a for loop and I check this one. Is it 3? Nope. Is it 3? Nope. Is it 3? Nope. Is this 3? Yes, right? To where I have to check the entire thing. I have to check every single value. That's O of n, right? And so as n increases, you could see as our array increases and gets much larger, the time it takes to actually run this is, quite a bit more. Now we also have O of n squared. And so that's kind of, that's even worse, obviously, right? That's our nested for loops. Right? That's our nested for loops. If I've got 2 for loops that I'm iterating through, and I have to iterate through each one every single time, that's going to be O of n squared. And again, as n increases, I double the amount I have to do in squared to, because I have to iterate through each for loop, each time. And that is O of n squared. Again, those are nested for loops. We have an O of 1, which is our constant time. Can anybody remind me of a situation when constant time would be?
Just return the constant number.
Yeah, so like if I've got a 1, 3, 4, 7, and all my function does is it returns the array at the first index, right? The index position 1. It doesn't matter how large n is, right? It could be 1 billion values. I'm still just returning this first index, no matter what, right? And so O of 1 is, hey, it doesn't matter. The time it takes for this algorithm to run is not affected by the size of my array. And that's what we call constant time, meaning that, hey, it's constant. No matter what, it takes the same amount of time. Time not being the actual milliseconds it takes, but it's just saying from a functionality standpoint, it doesn't change if we have, 5 things or 5 million things. We're still just looking up at index 1 and looking that up, right? Now, one we haven't talked about, but we are going to talk about today is log of n. And log of n looks something like this, where we are coming up and it kind of comes up and then it peaks. Are you guys seeing my whiteboard? I shared a whiteboard.
I see a whiteboard, but I can't see anything changing. I don't know if that's just a me problem.
I think I see it like lately. It came through though.
I know the whiteboard, you can like move it and go on different parts. Are we
Can
anybody
you
else?
like different color?
I see big O equals log n and then the little graph you made.
Yeah, that's what I'm, and I see some people made some edits, just as you guys know you can. So I don't know.
Oh, sorry. I'm just seeing navigate your
yeah.
workspace. That must just be a me problem then.
So I think you can grab and navigate around. It's like a huge space. Yeah, and then there's a magnifying glass on the back left.
Yeah, it's not doing anything for me. I'm gonna hop out and come back in. Sorry, guys.
Okay, there's a
That's
little
me thing done.
hand, there's a little hand next to the magnifying glass and you can grab and move around. That might be the case. But yeah, if not, feel free to hop out. And this is being recorded, so you should be able to see it. Worst case scenario. Also, please, I understand that it's fun to draw things, but just for the sake of this. Okay. So the third one we want to talk about, and there's other ones, there's like exponential, so it's even worse. That's like a factorial, but is O log of n. O log of n, where it increases at the beginning, right? It increases at the beginning, but it sort of just levels out and it very minorly increases over time, right? It's not, please, again, do not grab. Thank you. Whoever just grabbed that, please refrain from doing that. So it's over time, it's going to grow and it's going to, but it's going to just grow very incrementally. And that's because of how logarithms work. So I told Colin, I don't even know if Colin's here, but I told Colin we'd go through the math about it today. So that's what we're doing. And hopefully this gives you an idea of how logarithms work. So if we are looking at sort of the definition of a logarithm, so if we're talking about a definition, it could be said like this. And sorry, I got my notes. I did some prep for this. Just want to make sure that everything was right. Where it could be said as log of b, so a base of x equals y. If and only if, that's what this 2i if represents, if and only if b to the power of y equals x. Another way we could do it that kind of makes more sense, and let's just do it this way, is in. So log of b, or so a log with a base of n equals y if and only if b to the power of y equals n. Now, if your brain's already melting, don't worry, it gets a little bit easier to comprehend. This is just sort of the base definition of a logarithm, and this is the math that shows how this works, right? Now, if you guys remember logarithms back in like algebraic, stuff back in school, you know that typically we used a base 10, right? So if you guys remember at all, math was your thing, we typically used a base 10 when we're dealing with logarithms, but what we do for computer science is we don't use a base 10, but we do a base 2. It's what we call a binary logarithm. So I'll just put a binary logarithm is a base 2. So what that means is when we're dealing with logarithms, we say log of 2, base 2 of n equals y if and only if b to the power of 2, or sorry, b to the power of y. Yep. Sorry, let me go back. Not b, because we just replaced b.
To the
If
power.
and only if 2 to the power of y equals n. And so this is sort of this is our definition. This is our expression that represents the logarithm. Now, because in computer science, we typically always do a binary logarithm, and it's always at base 2, we can actually drop this 2. And so it's just implied. And so what we can really change it to is log of n equals y if and only if 2 to the power of y equals n. And so that is really sort of the base algorithm or the base expression for understanding this. So really what we're wanting to know is, let's pretend that we've got an array of 8 values. What I'm saying is 2 to the power of what equals 8. And we know that 2 to the power of 3 equals 8. Because it goes 2 times 2 is 4 times 2 is 8, right? And so so let me grab this and move down a little bit and change this. Okay. So 2 to the power of 3 equals 8. And so if we're dealing with a algorithm that is operating in log of n time and space complexity, or let's even pretend, actually, let's go back. Let's pretend that we're doing binary search. If you guys remember yesterday, we talked about binary search. We talked about how one side is always, everything on the right is bigger than the current node and everything on the left is smaller than the current node. And we talked about how, hey, if there's a value, and we're looking for 5, we're going to check and say, hey, is 5, smaller or bigger than the current value that we have in our node, and we would eliminate half of that. So if we're representing that, let's pretend that we're dealing with this and we're looking for a certain value and we cut this in half, right? And let's say hypothetically, we just get rid of everything to the right, right? So that's just in one step, we've cut that in half. Now, again, let's say we do that. We cut this part in half, cut everything to the right in half. That's our second step. And let's pretend we're looking for 0. We cut this in half. We eliminate this. And now we found our value here. So even though n was equal to 8, it took us 3 steps or 3 iterations to find our value, right? And so we can see 2 to the 3 equals 8. And that helps us express how many steps it's going to take. Now, the power behind this is, let's pretend, let me erase some of this stuff. Let's pretend that this, instead of going to 8, it had 16 values in there. So we have 8, 9, 10, 11, 12, 13, 14, 15. Well, again, let's pretend we're working with 0 and we're walking through how many iterations is it going to take. Well, let's go to the middle. We cut the middle here, eliminate that side. We cut the middle here, eliminate that side, cut the middle here. Oops, sorry about that. My first cut was 1 off. Because we are going here. So we would go here and we would eliminate that side, right? Then we'd cut here, eliminate that side. We cut here, eliminate that side, cut here, eliminate that side. Now notice, even though n doubled, right? Even though the size went from 8 to 16. So now n is representing 16. The amount of steps that increased, or the amount of steps I had to do to get to 0, is just 4. So it only increases by 1. And we know that 2 to the 4 is 16. Now, what I want to reiterate is that when we are dealing with a logarithmic value, it's not as simple. It doesn't only work if it's if it only works with like bases of 2. So it doesn't only work with, 32 and 64 and, 128 and all that stuff. That's not what I'm trying to communicate when I'm saying 2 to the 3 equals 8, 2 to the 4 equals 16. But what you can see is that no matter what n is, it just really is one extra step to eliminate, because we're eliminating half of it, even if n is 1 million, right? If that goes to n is 1 billion, it's not that big of a change, because I think it's 2 to the power of 20 is around 1 million, and 2 to the power of 30 is around 1 billion, just over a billion. So really, to go from 1 million to 1 billion, which is a massive jump, right? To go from 1 million to 1 billion, we are only adding 10 additional steps, 10 additional things we have to do because we're just cutting in half, cutting in half, cutting in half, right? And so what O log of n represents, and it's a very, very good time and space complexity, is it's showing that, hey, even as n increases, and we see that this initial one is going from 2 to 4, 4 to 8, 8 to 16, right? As n increases, then once we get into the 128, the 256, the 512, and we keep getting much, much larger numbers, even though we are just adding one step and our numbers are getting much, much larger, it's not really incrementing our time, right? Our time isn't taking that much longer because we're just doing one extra step. Haptamu, you got a question?
Yeah. What if the number of nodes is odd? That's
Yeah,
one
that's
big-
yeah. So I already stated that it's not just an even number. It's just a this is not, I'm not saying that it's got to be, you know, a base of 2 and only works for 16, 32, 64, all that. It's just representing that we can always, it's just one extra step. If we're cutting in half and getting rid of, doesn't matter what n is, even if n doubles, even if n is, you know, 3 to 6, it doesn't matter. It's just being cut. So even if our array, let's pretend our array, let's get rid of this.
Yeah, I mean, like, how do we know the half of that? Like, it's now even.
Well, remember,
Uh,
you're just getting a node, right? And so if it was 8, we're just picking the left or the right. We're seeing, is it bigger or less than the number we're looking for? And then we eliminate the half that doesn't matter. So let's pretend we had a value, and these are all binary search is one of the big ones for this. Let's pretend we had, you know, we had 1, 7, 9, 11, 34, 42, 56, and 71, right? Well, when I'm looking at this, if I'm doing this, let's actually add one more. And we'll add 99. What I would do is I would look at half of this array and I would find the index or the value, right? And we could either do, because this is odd, because there is an odd number right now, it's 1, 2, 3, 4,
9.
5, 6, 7, 8, 9. Yeah, so n equals 9. Right? And so what I would do is I would get a value of, I would get the half point. So in this case, I would look at 34. And let's say we're looking for the number 56. Right? I would look at 34. Again, it doesn't, n is just 9. And we're going to say, hey, is our current node which is 34, is current node, I'm going to put CN, greater than or less than 56. If it's less than 56, well, I know that everything to the left of my current node, which is 34, is going to be less than 34, right? So I don't need to look at that, and I can eliminate, actually, I eliminate 34 in the remaining values. Well, I would also check and say, you know, is my current node equal to my number? And then if not, I would say, is it less than or greater than? And because it's less than, I'm eliminating the half. So then I'm going to come here and I'm going to move to half of this. And I'm going to, you know, here I would have, and because I have an even number, I could pick either left or right. It doesn't really matter. If I picked the right one and I'd say 71, I'd say is my current node, which is no longer 34, but now is 71. Hey, is that equal to 56? It's not. Okay, is it less than or greater than? Well, it's greater than. So if it's greater than, then I know that anything to my right is going to be greater than 71, and 71 is greater than my current number, so I can eliminate anything to the right.
Mhm.
Then I would cut in half. Again, I pick left or right. I would pick, let's pretend I picked left. I'm going to check, is 42 my number? It's not. Okay, is it less than or greater than? Okay, it's less than. There's not anything remaining, but if there was still, like, let's say this was a massive array, I would cut everything remaining to the left. And then I would pick and grab this value. And then I would say, hey, is my current node, which is currently 56, is that equal to 56? Right? And then I
Okay.
would, and then I'd say, okay, great, we're good to go.
So it's a sorted list already, right?
Sorted, yes, in the sense of it's, so sorted is this is a sorted array. Remember, when we're dealing with binary search trees, it's not inherently, it's sorted in the fact that anything to the left is smaller, but it's not sorted, if that makes sense. Like we know it's got to be smaller, but it's not, we
Okay.
could have a 20, let's say that's my root node, and then here is 19. And then my 19 could have a 5, and well, 19 wouldn't be a good one. Let me delete this. Let's make this an 18. It's got a 5 and 18. And then to the right is 19, because it's got to be bigger, right? Anything to the right has got to be bigger than the node, its parent node. And then here could be 3, and this could be, 17. So it's still less than, so it's not necessarily, and then this could have, 2 and 16. I guess it couldn't be 16, but so it's not inherently sorted is what I'm trying to communicate. It's
Yeah,
not like
I get
sorted
that.
as in like 0, 1, 2, 3, but we know that everything to the left of this node is going to be smaller, right, than 20. So I can, if I'm looking for 25, I can actually get rid of all this. I don't even have to look at it because I know it's got to be less than this node here.
Okay, and that
Does that make sense?
makes sense when we like cut in half in
Mhm.
that list or array. We know the left side always less than to that node, and the
Yeah.
right. Okay.
Yeah. So because this is a sorted array, which that was just to give you an example, because this is a sorted array where, and I was trying to represent, everything to the left is always smaller, like it got sorted, from least to greatest. Everything to the left is smaller, again, to represent a binary search tree. So then we could just eliminate it. I could have done the same thing. I just didn't want to build out a tree. It's a lot easier to build out an array that's sorted.
That makes sense. So that like the binary search is the of log n, the big
O
O
of log n. Yeah, because we saw, right, even as n increases, and if it goes from 8 to 16, it goes 2 to the power of 3 and 2 to the power of 4, right? And that's just to represent, again, it doesn't have to be a base 2 in value. It's just to represent that even though this doubled, and there's a delta of 8 here, this just went up by 1 value. So it's
Okay.
just to represent that even if n
Yeah.
squares itself, right, even if it doubles, we're just gonna go up by 1. And so
So-
that's where the log of n represents that.
So for recursion, same logic like big O notation log n, right? For recursion, same as
Not
binary.
always, depends on what's in your recursion.
Okay. Okay.
So like if you've got a function that that iterates through everything, and then you use that in recursion, it wouldn't be a great, but that's just an example. You're still doing log of n, right? You're still, or not log of n, sorry, O of n, because you're still iterating through. So recursion, can be O of n. It depends on what it's doing.
In binary search, we do search, insert, replace, delete. All the same thing, same concept.
There's a little bit, we're gonna build out some code for
Okay.
that. So it's not necessarily the same concept, but we are gonna use recursion, to build, because we have to iterate through our tree in order to make sure that we're putting things in the correct order. So that way, when we are retrieving and searching through things,
Yeah.
it's faster. One thing I was thinking about today, data structures are just ways we can set up our data. And knowing what our problem is, we can set up our data in a way that is more efficient and more effective for searching or solving whatever problem we're trying to do, right? And so again, you can do a lot of the same stuff in different data structure is just how we structure our data. I mean, it sounds so basic, but it's just really how we're storing and structuring our data. And we know, okay, if we are building a Spotify and I want to have a next and a previous value, well, then when I'm building out, let's say we're thinking about a project that implements this, and let's say I've got a user and there's all these songs, they want to build a playlist. Well, the way that I could store that data is I just take a song and I do the first one is my root node, right? Or my head in this case for a list. And then I'm storing that and I'm adding a prev and a next. A prev would be null if it's the first one. And then a next value is just the next song or node that's holding that song's information. And then they can travel back and forth because it'll have a previous, which is the head, and it'll have a next as well. And so it's just a way that in my algorithm, as I'm setting it up, if instead of pushing to an array or doing that, I'm actually just building a singly linked or doubly linked list. It's just a way I'm still dealing with the same data. At the end of the day, I'm still dealing with just a song object. How do I want to store that object is going to be dependent on what am I wanting to accomplish in my project or in my program or in my whatever I'm trying to do here. Does that make
No,
sense?
It make more sense now. Like the reason I'm asking was like the time complexity with the binary search for create, search, extract, or update. Is it something similar or is it different? No, I think it makes more sense now.
Yeah, it's
Based on-
similar, right? Because if I'm going to insert a value, let's say I'm at a root 20. And we've got, I'm just gonna make this quick, 18, let's kind of do what I had. 18, 19, 5. Here I've got 31, 28. I've got 42, and I've got 53. Well, let's say I want to insert the value. So insert the value of, 71. Well, I'm going to look at my root node and I'm going to say, okay, is there a root node? If there is, great. Is it less than or equal to, or is it less than, greater than, or equal to 71? Right? And if it's because it's less than 71, I already am eliminating this. I don't need to traverse that way. Right? So I'm going to traverse to my right. There's not a space where we're going to iterate through please stop. There's not a space where we're ever going to iterate through everything, because unless we had a tree that had, a root node of 7, 73, and it just had one side and one side and one side, and that now it just becomes basically a singly linked list. Right? And we had to iterate through every single one because it was always just less than, less than, less than, less than, less than. Then we'd have to iterate through every single one. And that again becomes just a singly linked list.
Yeah, it's clear now. Thank you.
Yeah, of course. Okay,
I didn't realize that would mess stuff up. I'm sorry, Will.
you're fine. You're okay. Okay, my friend. I get it. I would do the same. Okay, so I just wanted to show really kind of how the math works. Really, at the end of the day, what I'm trying to communicate is seeing that in relation to as in increases, our logarithm, there's not that much needed, right? So if I have 2 to the power of 0, I believe that's 1. 2 to the power of 1 is 2, so that doubles. 2 to the power of 2 is 4. To 3 is 8. To 4 is 16. To the power of 5 is 16 times 2, which is 32. And we went from 1 to 32 in 5 steps. We have 6 steps technically. Versus O of n, if we had to iterate through or increase from 1 to 32, the difference is we'd have to do 31 extra steps, right? If we were going to go through the entire thing of O of n, we're going from n equals 1. Okay, well, oops, let me go back. N equals 1. Okay, well, if I'm iterating through the entire thing, that's not that big of a deal, right? I'm just going through 1. Once n equals 32, now I have to check 31 other, I have 31 other steps. I have to check 31 other values versus a logarithm. You can see that very quickly. Like if I do 2 to the power of 6, what is that? 64, and then 128. And then what is it? 256, 512. And then we're up to over 1,000, right? But you can see that that's just 2 to the 6th, 2 to the 7th, 2 to the 8th, 2 to the 9th, right? The difference between these is 10 steps versus 511 steps. And that's why log of n is much, much more powerful, right? It's much faster, much more efficient if we can do that. And that's where binary search tree really comes in handy. Does that make sense to you guys? Just kind of visualizing, okay, here's the algorithm, here's the math. Yeah, Uptime, go ahead.
So which algorithm, like I know it's based on the type of equation, like compared to binary search, recursion, or what would that linked list or double? Which one is more for higher computing equation?
What do you mean by higher computing? Do you mean which one is
Like,
more efficient or which one
Yeah,
takes longer?
based on the execution time. Like I know the data science people, like they have like high computing formula, like mathematical equations.
Mhm.
When we
Yeah, so
compare,
data science would be inherently, I mean, there's some things that they might do things differently. In the way that they kind of handle, because they're dealing with probabilities and more statistics. This is more so just talking about, okay, the way we store data, how quickly is it to retrieve it, to iterate through, kind of, again, thinking through if we're building an app that is a music player, how are we going to store that data in a way that's the most efficient, right? And part of the job, honestly, is that maybe somebody stored your data in an array and that worked because they were just bootstrapping and trying to get it going. But you're like, hey, I could actually optimize this and put this in a singly linked list. I could put this in a binary search tree, whatever, and that'll actually be much, much more efficient. It'll give my user a better experience. The download times will be much faster. So it's called refactoring your code. Refactoring code is another part that you might have to deal with. So in terms of what's the most optimal, so if you're looking about, again, remember, these are all worst case scenarios. When we're dealing with big O notation, we often just say, what's the worst case scenario? So when we're dealing with worst case scenario, it goes from here, O of 1 is the most optimal, right? Because it doesn't matter. Then it goes increasingly up as, so log of n is better than O of n is better than O of n squared, and then O of 1 factorial, which is like O of n exclamation point, is by far the worst.
Yeah, I get it now. Thank you.
Yeah. Yeah, of course. Anybody else have questions on the mathematics side? And then we'll jump into binary search tree. We'll actually build one out. Cool. Well, let me stop. So yeah, Duntrail, that's a great question. So if you were to say, so to skip a song is next dot next. Yeah, exactly, right? If you put skip, maybe, so it could either say, let's say you've got an array, or sorry, a doubly linked list that's got song 1, that points to song 2, points to song 3, that points to song 4, right? And you want to skip 3, well, it could, what it might do is might go in and say, hey, I'm going to update the dot next value of 2 to this node's dot next value. So now really what's happening is we are, instead of our arrow pointing to 3, it now is pointing to 4. Same thing with like on Spotify, you could do like a add to my queue. So even if you're playing a playlist and you add it to the queue, what it probably does is there's, you know, a list in your queue. Technically, I think it, even if you're playing a random playlist, my queue shows up. And then really all you're doing is you're adding to this and saying, hey, I want to add this value into this list. And then the way you change it is you're just changing where it appears, right? And so what's pointing to what? Yeah, great example there. Cool. Okay, doke. I'm going to clear this page. I'm going to stop sharing this. Let's go back to our actual code. Okay, so let's talk about actually building out a binary search tree. Now, we're not going to get a ton of time on this. I will post my code to GitHub, and then you guys can look at it if you want. But if I got a binary search tree, what I'm going to do is I first need to, you know, our binary search tree is made up of nodes. So I'm going to say class node, and I'm going to let ChatGPT come in and handle this, is I'm going to have a constructor. That constructor can take in some data, again, a value, it's a 5 or it's a 20, whatever. I'm also going to say left equals null, right equals null, and then change these values. So that way, instead of having to, instead of having to like create a node and then assign it, I can actually just assign it and create it in the same one. Cool. So I'm creating this class of node. This is no different than we did when we did a singly linked list, right? Where we had this node and it had some values. It had the data that it's holding, what's to my left and what's to my right. And so if we're thinking about what this looks like visually, it's really, I've got a node and it's got a pointer, right? And let's say I create the node of 5, or maybe we'll say 50 to make it easier. It's got a left, which right now is null, which, you know, if we, it would really kind of not have anything there, but just for, you know, understanding's sake right now, it's got null to the left and to the right. And if I were to create another value, that's maybe 25, it's going to check this. It's going to say, hey, are you greater than or less than 25? You're greater than. It's going to check and say, is your left null? If it is, well, then let's replace that with our 25. Oh gosh. Let's rewrite it. I was trying to be fancy. Let's replace it with 25. And so that's how we're going to kind of iterate through this. Okay. So we've created our node. Now let's go ahead and create our binary search tree. So I'm going to call this, binary search tree. Binary search tree. And this is going to have a constructor because we need to create this. And we need to have a root, right? Our starting point. Again, just like a singly linked list, this is just like our head, but we are going to call this our root. Now within this, we are going to use our handy dandy encapsulation for all the things that our binary search tree can do, right? So the first thing we're going to do is we're not going to do this helper method yet, but we're going to insert a node. Cool. So we are going to create something called insert. That's going to create a new node. Nope, I don't like this. Sorry. I'm gonna change this up. So I'm gonna call this insert node. And this node is gonna take in some different values, right? Because I want to use recursion to build this in. So I need to take in our node and our new node. And we'll see what that means here in a second. So what I can say is, hey, if new node, if new node.data is less than node.data, and we'll see how this kind of comes in here in a second. Then what do I want to do? I want to check to see if node.left is equal to null. If it's not, or if it is, then let's set it to new node. Else we're going to run this and keep going till we find an open space on my left. What this is doing is I'm creating a function or a method in this case, because it's associated with a class called insert node. It's going to take in my current node of where I'm at. And it's going to take in the new node that we have. Right? It's going to take in the new node that we have. Now we haven't created, we'll see. Give me a second because we're gonna sorry if there's a little confusion. We're gonna have a helper method that's going to help this out. And what it's checking is basically saying, hey, if the new node that I have, in this case the 25, is that's less than, let's pretend we're here at 50. If that's less than that, then I want to check 50's left node and say, hey, is that equal to null? Just like we had here. If it is, then let's set it to new node. If not, let's run this again with the next node. So in this case, if I was wanting to do the number, 21, well, now it's going to run this function, the same ones we're using recursion, but instead of our node, we're passing in 25, right? So it's now going to come here and say, hey, is this value less than or greater than my new node's value? And we're going to keep doing that to find the correct place where this is going to go. Cool, let me erase this. Cool. So that is if the new node data is less than my node's data, right? That's if 25 is less than 50. But we have to handle, if it's not, well, then what are we going to do, right? Then we're going to check and say, well, then we can assume that it's greater than. And so then we're going to say, check our right, and we're going to keep doing that down to our right. So we're using recursion here to check and say, hey, is this, is it greater than or less than? And we're going to traverse through our tree. And each time we do that, even if it's less than or greater than, we need to keep traversing on left or right. And then we are going to insert wherever we're there, wherever that is. Now I said that there's going to be a helper method. And maybe I'll just create this and then we can deal with this. Okay. So this is us inserting so I know I'm going a little fast. I'm just running a little bit out of time. Let's pretend first and foremost that we don't have anything. We just have a binary search tree because we called BST, a binary search tree. And so we have a null value, right? We have nothing there. Let's pretend I want to add the number 50. We're going to run insert. And it's going to create an instance of my node where data equals 50. My left and my right are going to be null. Cool. It's going to, so now we have our node. Then it's going to say if this dot root, this is associated to this binary search tree. And so if I were to say, BST equals, if I were to say something like, this, and if I were to say, BST dot insert 15, and I'm saying this instance of my binary search tree, if this dot root is null, which at this point it is, right? Well, then let's go ahead and set the root to the new node. So because it was null, now our root is just 50. Now let's pretend we add in another one and we want to add the number 15. We're going to run bst.insert, pass in 15. It's going to create the new node of 15 that's got a data of 15, a left and a right value of null. And it's going to check and say, hey, if this dot root equals null, well, then let's set the root there. Well, it doesn't equal null, right? Because this dot root is now equal to 50. So it doesn't do this. Then it says, okay, we'll run on this instance of my BST, run insert node, and you're going to pass in this root as my node that I'm currently looking at. That's where I currently am. And my new node, which is what we just created. So then it's going to say, okay, great. If new node.data, which is my 15, is less than my node.data, so if 15 is less than our 50, then I want to check and say, well, does 50 have something to the left? Or is it null? In this case, it's null. So it says, okay, well, then add in 15 here. So then now my value is 15. Then let's pretend we say, okay, we added 15. Now let's add in the number of 16. Okay. Well, then what it's going to do is we're going to run BST. So we've got, let me delete this stuff real quick. So far, we have done sorry, 50, that's my head, 15, and 16, right? You're inserting these values, and maybe I might have a function that takes in, if I'm doing like a song, I have a function. Within that function, I do my insert. So now we already have our head at 50, and we have a left value here at 15. I still have nothing on my right. The value, the node of 50 still has nothing on my right. But then now what it's going to do is we're going to run in BST insert 16. So again, we're running insert. We're creating a new node of 16 that's got a left and a right value of null. We're checking, hey, is this the beginning? Nope, it's not. Okay, great. Let's run insert node. And it's going to say is node, and we're going to pass it the root. So we're starting here always, right? Is our new node data less than, so is 16 less than 50? Well, it is, right? then it's gonna say, hey, if the node.left, so 50.left is equal to null, well, that's not true. So we go into our else and we use recursion to run insert node again. But instead of starting at 50, we're now passing in our node left. We're going to this 15. And we're saying, okay, great. If new node, which is still my new node, so if 16 is less than 15, well, that's not true, right? It's not less than, so it must be our else. And it's going to say, hey, does node dot right equal or node, which is representing 15, does its dot right value equal null? Well, it does, right? So that I'm saying, okay, my new node or my node dot right is now my new node. So now this goes to 16. And so we can traverse, and it's just using recursion to keep finding where's the correct spot where this is going to be. Does that make sense? Any questions on this?
I have a question. So
Yeah.
it makes sense what you said, but say you did 17, would it go in between 50 and 15, or would it go to the right or left of 16?
It would go to the right of 16, right? So if we were going to do 17, let's just walk through it, right? We're going to run insert. We're going to create a new node that's got a left and a right value of null. We already have a root, so we don't have to worry about it. It runs this, and it's going to start at 50, and we know that it's less than. And it's going to check here, and it's going to say, hey, is the left value here empty? No, it's not, because it has 15. It says, okay, let's traverse to 15, right? Runs this again. Now that the node is 15, it's going to, that's the node we're on. It's going to run this insert node with 15 and 17. And then it's going to say, if the new node.data is less than, well, it's not, right? 17 is greater than. So it's going to come down here and it's going to say, does this have, does 15 have a right value? If it does, well, then we need to run this again. And now we're going to, new node right is going to equal 16, right? It's this node. And so now instead of this being 15 and 17, we are 16 and 17. And again, it's going to check and say, hey, is 17 or new node.data less than our node.data? No, it's not, right? So we come down here and it says, okay, well, does 16 have a right value or is it equal to null? Well, it's equal to null. Okay, now let's set 16's right value to our new node. So then we would have 17. Does that make sense?
Yeah. Yeah, I was just wondering if it, if the number was higher than what it started at. But basically, in the Binary search tree, once you create the 15, now you can't basically go in between. You have to do the logic of is it left or right, and it's always
Yeah.
gonna build. It's never gonna be able to like get ahead of 15 or
Mm-mm.
the other way. It's always just gonna do another branch.
Yeah,
Check
because
that,
in
left or right.
yeah, I mean, in theory, right, this could be 1. Oops. I deleted everything but the thing I wanted. This could be 1. And then we could go to the right, to the right, to the right, all the way to 49, right? To where everything is still to the right. 49 is bigger than 1, but it's still technically to the left of 50 because everything to the left has to be less than 50. And then everything to the right has to be larger. So we could go, start from, this could be,
51.
yeah, well, it could be 1 million, right? I'll just put 1M. And then in theory, this could go to 999,999.
To the left.
And then keep
Okay.
going to the left all the way down to, to 51. And so it's still
okay.
technically on the right, because the ancestor of this is 1 million. Everything to the left has to be less than whatever came before it. And everything to the right. So 17 always has to be less than this. Or sorry, greater than whatever value its ancestor, its grandparent, whatever. Right?
Yep.
It always has to be if it's going to be on the right. If it's on the left, like in this case, you couldn't have anything unless you had like negative numbers, like -1, right?
Right.
then, and you could go to, you know, negative infinity.
I
In
got you.
theory. But it's always got to be less than what is on top. So if it's on the left, it's always less than, can never be more. So this could never be, you know, 0. Because it's 0 is
Right.
greater than -1. Because if
Should
that
be
was the
on the right.
case, yeah. Yep. Which would be here.
Okay, yeah, that's exactly what I was wondering. Thank you for drawing all that up.
Yeah, of course. Any other questions, my friends? Okay. I'm gonna print this and I will post some code for if you wanted to remove a node, how we would do that. But I will post that in Discord, because it looks like we are at 5 o'clock and we have quite a few projects and I want to make sure everybody gets a chance to share. So I will stop recording here.